Okay, let's take a brief look at how we go about solving equations numerically and sometimes analytically, but obviously this is just an introduction, and the details of numerical methods are, there are many volumes of books written on them. I've mentioned some of the issues we have to worry about, like positive definitivity, positive definiteness is a better word, and artificial noise waves created by methods, and the time steps needed. There are many details, and we will look at some of those as we go along. Let's start with the advection equation we derived in a simple way. We said dc dt plus u dc dx is 0. So let's just stick to one dimension in space again. So the solution Cxt here can be analytically written. This is a linear equation, linear partial differential equation that we can solve for by setting the solution to be a function of x minus ut. Every time you see something like this, some of you probably can already think ahead and say that looks like a wave. So this is not a classical wave equation, but it has wave-like solutions nonetheless. So transport of function fx along the positive x-axis in a constant flow velocity u greater than 0 under the preservation of its form. So in this case, since u is constant, we are not creating any shocks. There is no nonlinearity in the system. So you start with the distribution of c along x with function fx looking this way, and the shape is maintained as we go forward in time. So this is u times t1, u times t2, so time t1, time t2. The shape is maintained, so you can see that that's like a wave. You can write a similar equation for a waveform that is propagating in the negative x direction, so that would look like this: dc dt minus u dc dx, where u is still positive, but you are going towards the left instead of the right. And you can have a solution now which is got the signal propagating to the right and to the left, so positive x and negative x. So you can use the double operator. So this is not multiplication, it's an operator. So d dt of minus u d dx acting on d dt plus u d dx of c. That gives us, if you solve for this, d squared c dt squared. U is independent of t, so you know that'll go to 0, and so on and so forth. Minus u squared d squared c dx squared equal to 0. And this is now a classical wave equation where you can look for solutions in x for c, as cx, the initial condition cx0 is given by the wave amplitude times e to the I kx. Some of you can already recognize k is a wave number in x. Of course, in the full three-dimensional atmospheric oceanic flow, you will have wave numbers in x, y, and z. So there will be k, l, and m as we go forward later on. The solution cxt looks is equal to a times e to the I k times x minus ut. So there is a frequency in it, amplitude in it, and a wave number in it. We can look at the summary of these quantities describing a one-dimensional harmonic wave with wave number k, which is just k equals 2 pi over lambda, where lambda is the wavelength, and that is 2 pi over k, where k is the wave number, and that's u, the flow velocity, divided by nu, the frequency. So that's the frequency 1 over t, where t is the period. Angular frequency is omega, so it is 2 pi over t. 2 pi is the circle divided by t. how many circles you make in a period, and period itself is 2 pi over omega, so we are in a tautology here, which is related to the frequency. If you've done oceanography, you probably know that things like period can be intrinsic based on the forcing and the projections it makes onto a particular waveform. Okay, so otherwise it can become a complicated function of Coriolis and other factors as well. Okay, so frequency nu is 1 over period, which is u over lambda. So you can see how they're all related to each other. So obviously when you solve for it, you have to know which is given, which is to be determined. So you always obviously have to have enough equations for enough unknowns, which in this case we have, right? Let's now quickly introduce ourselves again to a numerical solution. We looked at Taylor series expansions of derivatives, and we talked about approximations made as first order, second order in space and time and so on. So starting with our advection equation again, linear first order equation dc dt plus u dc dx is 0. We can do spatial discretization where x at any point is given from the origin by m delta x. So when m is 0, you are at the origin, and then you can go a step forward with m equal 1, 2, and so on. In the temporal discretization goes the same way, t equals to n delta t, with n going from 0, 1, 2. So you need to know the initial condition to integrate forward, obviously. So we can write c at any x and any t as c as m delta x n delta t, which usually written symbolically as c m comma n, and obviously this gets more complicated looking thing when you have three-dimensional c, right? So let's write a central difference approximation in time and space. So c m n plus 1 minus c m n minus 1. So at any x, so m delta x, you have time step plus 1 and time step minus 1. So you are at x and you are going one step forward, one step backward. You know the value at the previous time step because you already solved for it, and approximation for the current time in this second order approximation is dependent on the solution at the next time step and the previous time step. So we are kind of jumping the middle time step. This is central difference in time. Similarly, u times c m plus 1 n minus c m minus 1 n. So time n, you're going to the previous x and forward x divided by 2 delta x. Remember there's 2 here because you have taken two spatial steps and 2 time steps in either direction, and that should be equal to 0. So you solve for the next time step as the previous time steps minus u delta t or delta x solution at m plus 1 minus solution at m minus 1 n. This is referred to as Ctcs, centered in time and centered in space. It's also called Leapfrog scheme because even though we are solving for m and n, we have written the solution in terms of m plus 1 and solving it in terms of m plus 1 n and m minus 1 n. Obviously when you start at 0 you don't have n minus 1, so you typically start with a forward time step, and once you have the first time step then you can go 1, 2, 3 by solving this central difference discretization. This is called leapfrog because you are leapfrogging the current grid in space and time and using values in the previous grid, forward grid, previous time, and forward time. This has numerical issues. It creates artificial disturbances, waves in the system, and so on and so forth, but it is second order accurate. So here is an illustration of the leapfrog or Ctcs scheme on the spatial temporal grid. So you are solving for n plus 1 delta t with values at n delta t, but at m minus 1 and m plus 1, and with value at n minus 1. So you have to know this to solve for that, and when we start at t equals 0, we use a forward difference to do that. So Cm at 1 will be then Cm at 0, the initial condition, minus u delta t over 2 delta x, Cm plus 1, 0, minus Cm minus 1, 0. So obviously you have Cm plus 1 and Cm minus 1, the spatial value here and here known from initial value as well. Once you have the first step, time step defined, then you can go forward. So that's a very quick and simple introduction to advection equation, analytic solution, and numerical solution. Obviously, we are doing modeling because we don't have numerical solutions for the climate equations. So we will see more details as we go along. Okay. Next step is to look at the stability of these discretizations. When you discretize and start integrating numerically on a computer, you can have numerical errors that grow and create instability in your solution. The one is something I mentioned before in terms of creating unreal maxima and minima, or unreal negative values for things like humidity, for example. Okay, we'll look at that in the next podcast.